Now let us resume our discussion on limit and convergence. We already talked about what is the precise definition for limit of sequence or convergence of sequence. We say that a real sequence an converges to A as n goes to infinity if the following condition holds, and that condition reads kind of like this. For arbitrary positive real number epsilon, there exists a certain natural number n which depends upon epsilon, such that when small n is greater than that capital N, then the distance between A and A is less than epsilon. Roughly speaking, you can translate it kind of like this. The distance between AN and A gets arbitrarily small as the natural number n gets sufficiently large. Arbitrarily small is associated to arbitrarily selected positive number epsilon, which serves as a bound, and less than that epsilon. So an minus a is basically less than arbitrarily small epsilon. However, there's a middle part. That's when n gets sufficiently large. So an minus a may not be smaller than every epsilon. As a matter of fact, for every epsilon we can find out sufficiently large n that satisfies this condition. Yes, that's true, but not vice versa. Am I too confusing you? Well, that is associated to something like this one. If I throw away the middle part, sufficiently large part, this middle part, then we have example 4.2. We talked about this example before. This is when an minus a is less than arbitrary positive number epsilon without sufficiently large n part or anything like that. Nothing at all. In that case, what happens? An minus a is less than arbitrary positive number. That means an minus a has to be less than or equal to 0, because if it is positive, then it has to be strictly less than itself, because itself is a positive number too, and that's contradiction. No number is strictly less than itself. So what do we have? It cannot be positive number, so less than or equal to 0. Absolute value cannot be negative, so is equal to 0, and consequently what do we have? We have constant sequence. An is always equal to a. But then again, that's a bit too strong and not really interesting, and that's because all the middle part was snipped out. If you do put in this middle part, then we have something interesting, kind of like these examples we studied before. And in these examples, the key was to find out what is capital N, and we could algebraically manipulate 1 over n squared minus 0, or this n squared minus 1 over n squared plus 1 minus 1, and with some appropriate epsilon values, we can find out exactly what kind of bound we need, or something like that, which is a little bit more complicated. But then again, proving the convergence like this is rather tedious. Most of the time we use limit rules, and we're going to discuss the limit rules in a moment. But before that, let's talk about the theory. Okay, if we can find out capital N value which depends upon epsilon as an explicit expression of an epsilon, that's great. But then again, what if we can't? We know that it exists, we know that there is a dependence, but we do not know explicit relation. We can still consider that kind of situation graphically, and here is a nice example, and let me expand this graph so that you can see this behavior a little bit better. Now all these dots here represent the sequences an, and as we move to the right, we have all these an values which are y-coordinate values, and then we have actually 3 identical graphs of sequences with different color coding. And first color coding, the green one is associated to relatively large epsilon value. When epsilon value is relatively large, consequently, if it is okay to have dots within these two horizontal lines, green horizontal lines, in that case, we don't really need really large capital N value. As you can see, we have some gray dots on the left hand side, but after a while we have a bunch of green dots within this band, which means this condition, an is between a minus epsilon 0 and a plus epsilon 0, or distance between an and a is less than epsilon, is going to be satisfied. That's for epsilon 0 is about 0.5 in this particular example. So not so stringent epsilon condition, so not really large capital N0. Next picture gives you a little bit more stringent epsilon condition. We took a little bit smaller epsilon, and then the previous green solid lines are now de-emphasized with those dotted lines, and then let us concentrate upon the solid blue solid lines. And when n is greater than a certain capital N1, then an and a must be within epsilon 1 bound, and those kind of points are highlighted in blue in this picture. As you can see, capital N1 got a little bit bigger. Consequently, those blue dots, highlighted dots, are a little bit pushed to the right. If you look at the next picture, they are even more, they are pushed to the right even more. N2, the capital N became even bigger, and for those we have this epsilon condition. Distance between an and a is less than epsilon for smaller epsilon. This epsilon 2 is much smaller than before. And of course, if you take even smaller epsilon value, that'll simply means, well, pushing this graph or pushing these highlighted dots even further to the right, which means even smaller capital N value. And those kind of things exist, and those capital N values depend upon epsilon. You do not really need those explicit expression of epsilon. If you do have it, great, but you don't really need it. All we need is such capital N exist, and as you can see in this graphical argument, as long as we have an existence, then we have convergence. And this kind of thing is very, very similar to the limit of functions, which is kind of visualized as follows. Let me expand those graphics again too. Very same. As you move to the right, excuse me, what am I talking about? As you get smaller and smaller and smaller epsilon values, green, blue, and red, you see that you have to move a little bit further to the right in order to have the fluctuation within those epsilon bound, which are represented as the band, the strip captured in between those solid lines, red, blue, and green, in increasing order. And the definition is pretty similar. As a matter of fact, pretty much the same, except for one thing. Instead of an and a, we are selecting f of x and L because it's functions. And then, instead of capital N, we are selecting capital M. Instead of small n, we are selecting x. So far, not much difference. The only difference is this one. All the indices for sequences are coming from natural numbers, so that capital N should be a natural number. Here in this example, that bound M, the capital M, should be a real number because x is now a real number. That's the only difference. N and capital N are natural numbers versus x and M, capital M, are real numbers, otherwise identical. If you look at the pictures, visualization, again pretty much the same. Instead of dots, we have highlighted curves, and that's about it. In short, we're looking at some asymptotic behavior, horizontal asymptotes, either for curves or dots. And that's what limit of sequences and limit of functions and infinity do. So they're related, so they must be sharing some limit rules together. And then there's some. And let's see, we don't have enough time to prove any of those limit rules in this video, so let us just mention them. And we are going to prove some of them in the next segment of the video. How about the first one? Limit of constant is, well, just constant. Oh wait, this is so trivial that you don't really even have to talk about it. K always remains K. And then the next one is equally as trivial. If n goes to infinity, then n goes to infinity, the same. And the proof, yeah, okay, it's that simple. K minus K is constantly 0 because we have constant. And then, okay, this if you write down the proof, then it becomes rather complicated here. However, and if you just use your common sense, it's not difficult. If n goes to infinity, then n goes to infinity. Now the third one is not simple at all. Limit of 1 over n is 0 is something elementary, and it's really fundamental to other limit computations. But the proof is going to be very, very difficult. We don't do that here. I'm not going to dare doing that here in this course. Not even as an optional topic, no. Yeah, traditionally, this topic is covered in Real Analysis 1 Math 3000, but even there, students usually have tremendous deal of difficulty. So in some semester, I do it in Real 1, and some semesters I do it in the next semester. And the last time I taught Real Analysis 1 or equivalent, I didn't do that in Real 1 and went over to Real Analysis 2. That was before joining UNT Dallas, but I expect something similar here. So we are talking about something really hard, but just remember the result. Limit of 1 over n, that's going to be 0. 1 over infinity is 0. How about these limit rules? The first one and the second one are relatively simple, and definitely we are going to prove these two in the next segment of the video. These two are a little bit harder, so I'm going to leave those to interested readers. After going through these two, the first two, you'll be able to read through the proofs, I hope, if you are a sufficiently advanced student. And the third one is the fifth one is in completely different leagues, so I'm not going to bother that. This one really belongs to Real Analysis, or maybe even higher than that. And let's see, about inequalities, we have the usual rules. The first one, actually this one is easy, and yeah, we're going to prove that in the next segment of the video. And the sandwich rule, I'm not so sure we'll have time to do that. It's not really hard because if you simply use the previous one, then you can deduce it. So I may very well end up with dumping that over to exercises for students. So limit rules, all the limit rules apply, but the details are left to the next segment of the video. Now we have about a minute to go, so let's breeze through some of those limit theorems. And number one, oops, no, not that one. Number one, the uniqueness of the limit. If an converges a and also a hat, then a and a hat must be the same, which means there has to be only one limit. And this is an important step. It's not difficult to prove, and we'll prove it in the next segment of the video, but it's important. Easy but important, because if the uniqueness does not apply, then we have to throw away everything about limit. But luckily it holds, so limit is a worthwhile topic to consider. Next, monotone sequence theorem. Bounded increasing sequence converges to its least upper bound, and bounded decreasing sequence converges to its greatest lower bound. We talked about those before, and proof is actually written here in this notebook, but it's a bit too advanced, so I'm not going to talk about it in this video or next video, but interested students can go through with it. and the corollaries are there. And Cauchy sequence theorem, we're going to talk about it later.